Okay, so now I will do an important concept called independence. It's a very important concept, and it's so important that people assume it's easy and make mistakes on it. I don't know if I said that correctly, but so it's called independence. It's a very important concept. So we saw the example before. Let me write the example down again. So the example is the following. Suppose we toss a coin 3 times. Let's go back to our old coin tossing example. Suppose we toss a coin 3 times. Then we know that the sample space S is going to be equal to head, 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 tail, head, tail, head, head, tail, tail, and the tail, head, head, tail, head, tail, 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 head, and then tail, tail, tail. That's a sample space for 3 tosses of a coin. And I defined this idea that the example I did before was I said, let's say, let me call it event A, as event A was there are 2 or more heads in 3 tosses, was one event, and B was the event that the first toss is a head. And we had checked that the probability of A was a half, probability of B also was a half, but the probability of A given B was 3/4. So done earlier. So here are 2 events where of A and B, the occurrence of B affected the occurrence of A. Very nice. And this was our foundational idea of understanding conditional probability. Now I want to sort of discuss events where occurrence of one doesn't affect the occurrence of the other. So now let me do another example. So the above was an instance where the occurrence of one event affected the probability of occurrence of another, right? So in this case, that the occurrence of B enhanced the occurrence of probability. Now I want to do the following. I want to take a different event. Let's call the event C. Let's say the first toss is a head. And let's say the event D is the second toss is a head. So now clearly that A is just the first toss head is just that HHT, HHH, HHT. Then you just have HTH and then HTT. That's the first. That's the event that first toss. That's what C is. Second toss ahead is just allow everybody, right? HHH. Except the second toss will be fixed at head, and then just go. That's it, right? And then there's one more thing. There's one more, right? Just THH. Very good. That's it, right? Similarly, again here, probability of C is size of C divided by size of S, which is again 4 by 8, which is 1/2, right? And probability of D is again the same way. The size of D divided by size of S is again 4 by 8. It's again 1/2. Very good. Now, what is C and D now? C and D is the event that the first and second goes ahead. That means you have HHH, that's two elements there, and then you have HHT. And that's it. Right? And then, so you know probability of C and D is again the size of C and D divided by size of S. That's just going to be 2 by 8, and that's a quarter. Very nice. So now, if you go and do the chance of, you do two computations. So let's do two computations. So probability of C given D, right? That's the same as probability of C and D divided by probability of D. That turns out to be a quarter divided by probability of D is a half, and that's going to be again a half. So let me get this properly. So what we've shown is probability of C given D is also a half, and that's the same as probability of C. That's what we should have before, right? So the occurrence of D doesn't seem to affect the occurrence of C at all. Similarly, let's do the following. Let's do a simpler one. Let's do something like C and D complement is what now? D complement is that the second toss is not ahead. That is, again, that means C means the first toss is ahead. The second toss is not ahead. That means it's these two guys, right? So it's just, again, going to be HTH and HTT. Right? That's what C and D complement is. So you can also see the probability of C. Let me down here, better. Probability of, sorry about that. The probability of C given D complement is also equal to probability of C and D divided by probability of D complement. C and D complement divided by probability of D complement. And probability of C and D complement is 2 by 8. And the probability of D complement is again 1/2 because probability of D is 1/2. So it's 1/2. 1 minus half is 1/2. And this also turns out to be 1/2. It's also the same as probability of C. So what we're observing here is that the occurrence or non-occurrence of D, that is D or D complement occurs, does not affect the probability of C. The probability of occurrence of C. So what we are seeing is that the occurrence of one event doesn't affect the occurrence of the other. So in some ways that so no matter what happens, the probability of C is going to remain the same regardless of D happening or D not. So that means C and D are kind of independent of each other, which is what we'll formalize in the next definition. Sorry about that. So here's a very important definition in probability. So the definition 1.4.2. Here this is called independence. Independence. We say two events are independent of each other or independent if the chance of A and B is chance of A times the chance of B. So this is the definition of independent. So why the occurrence of C is same as occurrence of C given D and C given occurrence of D complement is by definition known to be independent if the probabilities match. So let me just rewrite the definition in terms of what was given above. So here I showed you that. So why is that definition equivalent to what I wrote before? Is that in blue, the probability of C given D is equal to probability of C is equivalent to the fact that probability of C and D divided by probability of D is equal to probability of C, and this step required that probability of D is positive. But if I use my little convention, then I can go back and say the same as probability of C and D is equal to probability of C times probability of D. So of course here in both these things I require probability is positive. In independence I don't require positivity. I just say that if this is true, this they call it. This is definition. So you say two independent events are independent if probability of A and probability of B is equal to probability A and B. So that is from two events A and B. Very nice. So now we have seen examples of independent events and examples of events that are not independent. In the previous example, so we saw that in the previous example C and D were independent, but A and B in the previous example were not independent. So let me just recap that. Right? So here I knew that independence is that A and B are independent. Here I showed you that C and D were independent, but A and B were not independent. Probably A and B was not equal to probability of A times probability. So this is a name. So you think of two events are independent if the conditional probabilities are the same as the original probabilities. So that's why you call them independent. Very nice. Now let's try and I want to dwell on these equations a little bit. Let me try and do that. So two events are independent if probability of A and B is same as probability of A times probability. Like that. Suppose we want to extend this to three events. Let's call this a star. Suppose we wish to extend it to three. Suppose we have three events. A1, A2, A3. And we want to understand what it means to say that three events are independent. So the question is, when do we say three events are independent? So one way to think about it is that you can just say that the formula star holds. So one naive way is the following. Let's do naive way. Let's do naive answer. Let's do first naive answer. You can just say, okay, I just take it as probability of A1 and A2 and A3, but by definition of the above is same as probability of A1 times probability of A2 times probability of A3. Okay. So now this is an issue now, right? So now, if can I just say this to say that three events are independent? So here comes the clash between the intuitive notion of what we think is independent. Independent means that that kind of the conditional probabilities sort of give the original probability. That's why we call it independence. But is this enough to do? But we definitely want this. Is this enough? In some sense? So let's do a simple example to see that this may not be enough. You need more. So you need more to assure three events are independent. So let's try and see a simple example. So let's do the example 1.4.4. So suppose we toss a coin 2 times. Suppose we toss a coin 2 times. Coin 2 times. So you toss a coin once and toss a coin again. Okay? And let's say toss a fair coin. So the probability of heads is half, the probability of tails is half. So then you'd say that A1 is equal to head and this tail, right? And A2, let's say the event that you get a head in the first toss. And A3 is the event, let's say you get head and then tail head in the second toss. So A1 is the event you get heads or TT, that is 2 heads or 2 tails. A3 is the event you get one head in the first toss, no one in the second toss. A3 is the fact that you get a head in the second toss. Then one can easily see that probability of A1 is equal to probability of A2 is equal to probability of A3. So there are 4 possibilities in the sample space, and you have 2 of them, so it's 2 by 4, and that's just the half. So they're all the same. Then probability of A1 and A2 is what now? And probability of A1 and A3, they're all the same, because if you look at it, and A2 and A3, so A1 and A2 has only one element in common. A2 and A3 again have one element in common. A1 and A3 again have one element in common. They all have only H in common. Right? So it's going to be 1 by 4. Is that clear? Okay. So from the above, this clearly implies that probability of AI intersection AJ is the same as probability of AI times probability of AJ for 1 less than equal to I not equal to J less than equal to 3. That's just straightforward, right? You just multiply the two things, half and half is a quarter, and all the intersections are equal. So this clearly implies, so we're in business now, we can clearly say now that A1 and A2 are independent. Or let me just go a little bit before. All the pairs are independent. That is AI and AJ are independent. And then for I not equal to J. Now comes the crucial part. So I wanted to understand what more do I need, right? So one idea could be that I have probability of A1 and A2 and A3 is equal to this, and all the pairs are independent. That's one idea. But that may not be the case, because you look at this guy, but you look at probability of A1 and A2 and A3. So what's the common intersection of all three? It's just head, right? So it's just probability of the event head. And that's just 1/4. So probability of A1 and A2 and A3 equal to probability of head-head is 1/4. So this implies that probability of A1 and A2 and A3 is not equal to probability of A1 times probability of A2 times probability of A3. So in some sense, if you have three events and they're all pairwise independent, that's not necessary to guarantee this third equality. So you can't have this. So going back to our investigation, what's going on? So if you want to know three events independent, it may not be. One thing is that if you just assume this line, it may not be enough because this doesn't guarantee the fact that the occurrence of A2 and A3 don't affect the occurrence of A1 and so on and so forth. So you don't know that. So you need more. One way to do more is you say, okay, fine, I'll go and say all pairwise independence. But that's not enough because pairwise independence doesn't imply this equality, which you would like to have. So here is the summarizing remarks. So A. So it's tempting. It's tempting to do the following, that let me call this as dagger. It's tempting to have dagger as definition of independence. For three events. This is because it's to mirror the probability of A and B is equal to probability of A and times probability of B for A and B independent. But alas, see, if you have two events independent, then they must be pairwise independent. So, but three events being independent, three events being independent should imply they are pairwise independent. But the above examples show the reverse is not true. The above examples shows pairwise independence does not imply that. That's the first factor. So pairwise independence is not sort of a global concept to assume three events independent, and three independent should imply pairwise independence. That's something we understand. So we need to be careful about what we mean by three events being independent. So here's the fundamental observation. See, I don't know if you realize this. I just wrote down star, right, for probability of A and B equal to probability of A times probability of B as being two independent. But when I did the example for you, I said that probability of C given D is half. Probability of C given D complement also is half, and they were both probability of C. That's when I concluded that C and D are independent. That is, the occurrence of C and doesn't depend on the occurrence of D or D complement. But then in the definition, I somehow wrote down only one equation. Probability of A and B is equal to probability of A times probability of B. Somehow I was a little glib. I just didn't clarify to you why one equation was enough for independence. But here's the mathematical sort of justification for this. Why this is enough. Star actually is 4 equations. So let me write that down. So what is it that we need more? star, which is probability of A and B, is equal to probability of A and probability of B, is actually 4 equations. Because from this, you can just check. This will actually imply and be implied by probability of A and B complement is probability of A times probability of B complement. Is actually also equivalent to probability of A complement and B be equal to probability of A complement times probability of B, and is actually equivalent to probability of what's the last one? A complement and B complement is equal to probability of A complement and probability of B complement. That means A and B are independent if complements are independent, or A and B complement independent, or A complement and B independent. So that one equation gives you 4 equations. But in the 3 case, it doesn't do that. That one equation doesn't give you all 8 equations. So that's the definition you will need for mutual independence. Let me write that down. End the class. So definition 1.4.5. This is called mutual independence. It's a very important definition, so keep it in mind. A collection of n events, a finite collection of n events, say A1, A2, up to AN, is mutually independent. If probability of E1 and E2 and E3, sorry, or A1, I use A1, right? Probability of A1 and A2. I want E1. Sorry about that. So I want E1 intersection E2 intersection En is equal to probability of E1 into probability of E2 into probability of En, where EIs are either AI or AI complement. I mean, this is like a collection of 2 to the n equations that must be true for independence. So this is like a collection of 2 to the n equations. So for the 3 case, you will need 2 to the 3 equations, that is 8 equations to guarantee independence of A1, A2, A3. You want all the complements and them to be also involved. Very nice. Now we can also generalize a little bit. An arbitrary collection of events AT, T in some index set I. So for some index set I is mutually independent. So an arbitrary collection is independent if every finite subcollection is independent. If every finite subcollection is mutually independent. Yes. So let me just quickly recap independence for you. So we began with the following idea that we had an example of tossing 3 coins. We knew before that if you have A is the event, there are 2 or more heads and 3 tosses, and B was the event, the first toss is a head. We knew the occurrence of B affected the occurrence of A. Hence, probability of A given B was not the same as probability of A. So then I said, okay, fine, let's do something else. Let's use the kind of independent functionality. That is, the first toss doesn't affect the second toss in some sense intuitively. So I defined 2 events, C and D. C was the event, the first toss is ahead. D was the event, the second toss is ahead. Then I found out the chance of C was half, the chance of D was half, and the probability of C given D was a half as well. So was the probability of C given D complement, also a half. They both match probability of C. Very good. That means the occurrence of C, not the occurrence of D, or the occurrence of C, occurrence or non-occurrence of D, does not affect the probability of occurrence of C. So that is what we think of as independence between 2 events C and D. Okay? If the probability of C given D is same as probability of C given D complement, the same as probability of C, we will say that C and D are independent. That's what we think. So then I quickly turned around and said, okay, fine, I'm going to use this idea to define notion of independent of 2 events. So I said 2 events are independent if probability of A and B was probability of A times probability of B. So I use star as definition because I don't have to worry about probability of B being positive or 0. Because if I use conditional probability definition, then I'll have to understand that probability of D is positive to apply definition. But I've used this convention that probability of C and D is 0 when probability of C times probability of D is 0, or probability of 0, then I can use this line right here. So that's why I use the convention that 2 events independent if probability of A and B is same as probability of A and B. And if probability of B is positive and probability of A is positive, then I immediately know that probability of A given B is same as probability of A, and so on. So if probability of B is 0, automatically I assume that A and B are independent, no matter what A is. So now then I tried the fact that, okay, if I have 3 events, what do I do? How do I define independence? So one way tempting is from star is to write down as probability of A1, A2, and A3 is same as A1 and A2 and A3. It's sort of an intuitive way of sort of generalizing the fact that 3 events independent. But okay, let's do a check. We said we might need more, and why we need more is that okay, 3 are independent, we expect them to be mutually independent as well, pairwise. But then are they equivalent? So that we immediately check that I give an example of 3 events, A1, A2, and A3, which were pairwise independent, that is P of AI and AJ were P of A and P of A. But P of A1, A2, A3 was not the same as the product of A1, probability of A2, and probability. That means dagger did not hold. So pairwise independence does not mean the events are mutually independent. And the observation for that was that the star out here was one equation, but actually it had information about 4 equations because they are equivalent. You can try and show the simple exercise to show that probability A and B is equal to probability A and probability B times probability B implies the other 3 equations and vice versa. So that got us the definition of mutual independence. We say 2 events are mutually independent, or n events are mutually independent, if 2 to the n equation holds. That is probability of E1, E2, and En is equal to probability of E1 and probability of E2 and where EI are both AI and AI complement. And then we say an arbitrary collection is independent if any finite subcollection of them. So it's kind of a very important idea to understand that if AIs are independent means AIs have any combination of them, then the complements are also independent. And that is guaranteed by the 2 to the n equations and not by just one equation. And that's because in the n equal to 2 case, you wrote one equation down, but that contains information about 4 equations.